Hi everybody, I hope this video finds you well. In today's video, we're going to be working through practice number 7, which focuses on two major topics, expected value and the sampling distribution. Before working through this video, make sure that you've gone ahead and finished the videos on expected value and the videos on the sampling distribution, and also that you've had a chance to work through and try these questions on your own. If you haven't done that already, I would recommend pausing this video and trying some of these questions on your own. If you have already worked on them, well, let's go ahead and get started then. So for question 1, we're looking at a game, which generally means that we're going to be talking about expected value for our class. So in this game, we're going to suppose that you roll a 20-sided dice, so a dice with 20 sides on it. If the dice comes up as a 20, you end up winning $12. If it comes up as an 18 or a 19, you win $2. Otherwise, if it comes up anything else, you lose $1. So in other words, when you're playing this game, a 20 is really good for you, an 18 or 19 is sort of good for you, and anything else is bad for you, and you end up having to pay money to your friend. So we're going to do a couple things with this. First of all, with any type of expected value situation, we always start by having to build a probability model, and then we'll analyze a couple probabilities in B and C, and then finally we'll get to the main point, which is to actually calculate and interpret the expected value and decide whether or not this is a good or bad game to play. So let's go ahead and start with A. So we need to come up with a probability model here. So remember, a probability model is a list of the outcomes and their probabilities here. So if the outcomes for this game, of course, are that you could end up winning $12. So one of the outcomes could be plus 12 for us. One of the outcomes, of course, is plus 2, winning $2 here. And the third and final outcome is that we could lose $1, which is minus 1 from our perspective. Now, what are the probabilities going to be? Well, since it's a 20-sided dice, there are 20 possibilities. Only one of them ends up giving us that $12, so the probability there would be 1 out of 20. Two different things give us the $2, so that's 2 out of 20. And everything else makes us lose $1. Now, how can we find the remaining thing? Well, if we think about it, we can just take away the stuff that we already have. 1 and 2 is 3. Take that out of the 20 overall, and that means that the 17 remaining outcomes have to be where we lose. Remember that this is a probability model, which means that these probabilities have to sum up to 1. And that's what we're using to get this last probability. We're saying that this is 1 out of 20, this is 2 out of 20, that adds up to 3 out of 20. So what remains, 17 out of 20, must be the chance of losing in this situation. Okay, so now that we have our probability model, we can answer some follow-up questions. We want to know, what's the probability we win money on one play? So if you're going to play this game just once with your friend, what is the chance that you end up winning money? Well, as we can see, you can win money in two different ways. You could win $12 or you could win $2. We can just add those probabilities together. So 1 out of 20 plus 2 out of 20, and that equals 3 out of 20. So the chance that you win money on a single play is 3 out of 20. If you want on a calculator, you can check that that comes out as 0.15 or 15%, meaning that when you play this game, there's only a 15% chance that you win money. Okay, let's go ahead and look at C. What is the probability that you lose money on 15 plays in a row? So we want to know the probability lose money on 15 plays in a row. Okay, so in general, when you see this language of losing or winning a bunch of times in a row, the way we're going to approach that is we're going to take a look at the chance that you lose money on one play, and we're going to raise that to the 15th power. What we're really doing here is we're using that multiplication rule back from when we studied probability. And we're saying if we can figure out the chance that you lose money on one play, and that has to happen 15 times in a row, then we have to multiply that probability with itself 15 times. And that, of course, is what the 15th power does. So what is the probability you lose money on one play? Well, the only way you lose is $1, and that happens 17 out of 20 times. So this would be 17 out of 20, and then raised to the 15th power. Now here, this is probably easiest to actually do in a decimal form. So on our calculator, we can just type in in parentheses 17 divided by 20, and then raise that to the 15th. And if we do that, we should get approximately 0.087. So we can see that there's about an 8.7% chance, so a little under a 10% chance that you could go on a 15-game losing streak with this, where you lose $1 each time to your friend. Okay, so at this point, so far everything we've done has basically just been about probabilities. Now it's time to actually turn our attention to the expected value. Remember, even though this game so far looks pretty bad, I mean, remember, you lose 85% of the time and you only win 15% of the time. Remember that one of the ways you win is you gain $12, which is a lot more than losing a single dollar. So now we're ready to put all that together and look at the expected value. So let's do that here in D. So how do we calculate the expected value? Well, remember the key idea, or the key formula for expected value is you take each outcome, multiply it with its associated probability, and then add all those up. So this would be 12 times 1 over 20 plus 2 times 2 over 20 plus minus 1 times 17 over 20. So we're putting each of the values, how much do we win or lose, plus 12, plus 2, or minus 1, and then we multiply them with their associated probability, and then we sum all those up. So this is something we want to go ahead and just do on our calculator here. So if we do that, looks like we should get, after all that, looks like we should get negative 0.05. Okay, so what can we say from this? Well, the first thing is we can see that the expected value here is less than 0, which implies it's a bad game from our perspective. So in other words, what we've just figured out is that this is a bad game to play because we expect to lose money. Now, we can go a little bit further. Since we're asked to interpret the expected value, we can actually say how bad it is. We can say we expect to lose. And if we convert this into more of a money sense, right, 0.05 would be 5 cents. So we can expect to lose 5 cents per play on average. So in other words, when we talk about how bad this game is, we're basically saying that if we play this game a bunch, we expect that after we add up all our wins and losses to be losing about 5 cents per play on average. Remember, this language right here of on average is absolutely essential to have in your interpretation of any expected value, because obviously you never actually just lose 5 cents. Every time you play this game once, you either end up winning $12, winning $2, or losing $1. So this only makes sense as an interpretation when we include that language of on average. So what is the overall summary of this? Well, what we saw here is that even though one of the positive outcomes is much higher, plus 12 versus only minus 1, it happens so infrequently with a probability of 1 out of 20 that the expected value is still negative, so this would be a bad game to play from our perspective. All right, let's go ahead and take a look at question 2, which is also expected value, but has a slightly more complicated setup for the probability model. So I will go ahead and just look at question 2 by itself here. So question 2 says that there is a slot machine that consists of 4 wheels. The first 3 wheels each have 5 images on them: a spade, a club, a diamond, a heart, and a dollar sign. And the fourth wheel has 4 images: a red X, a blue X, a green X, and a jackpot. And the way that this slot machine works is that if it comes up 3 dollar signs and the jackpot, you win $200, which is good. 3 diamonds and a jackpot, you win $150, also good. $2 signs, a diamond, and a jackpot, you win $50, so still good. Otherwise, you lose $1. So we've got several things that we want to do with this just to reference our questions. Very similar to the previous one, we're going to start by constructing a probability model. We're going to do a couple of pieces of analysis with those probabilities. Then starting in D, we'll actually start talking about the expected value. We'll decide if this is a good or bad game. We'll also decide how to interpret the expected value if we played this game a bunch, which in this case means 1,000 times. And then finally, at the end, we'll figure out if we were going to try to make this game fair, in other words, not good or bad for either person playing it, for the person playing the game or the house or the casino, right? How should we adjust this payout to actually make the game fair? Remember, if the game is bad from our perspective, we'll need to raise this to make it fair. If the game is good from our perspective, we'll have to lower this to make it fair. So we'll see how to do that in part F here. Okay, so let's start with the probability model though. So for here, we need to do our probability model. Now, in the previous one, we could jump right to getting the probabilities because it was a 20-sided die and we knew there were only 20 possible outcomes, so things were very sort of simple. Here, the outcomes are not bad, right? We can say the outcomes, they're listed right here. If we get those $3 signs and a jackpot, we know that that ends up being plus 200. We know that if we get 3 diamonds and a jackpot, we get plus 150. We know that if we get $2 signs, a diamond, and a jackpot, we get plus 50. And everything else that otherwise is minus 1. But how do we actually get these probabilities? Because this time we can't just say, well, it's a dice, there's 20 things. We have to do a little bit more work here. The way to do this is anytime you see something with these slot machines, you want to use sort of some of your counting knowledge. Remember, in this case, we know that there are 4 wheels, so there's 4 possibilities here. Then we know that for the first 3 wheels, they each have 5 images. So there's 5 possibilities for the first wheel, 5 for the second, and 5 for the third. When we get to the 4th wheel, though, there are only 4 images, so there's only 4 possibilities. Remember, whenever you're counting and you're saying, I know the number of options at this moment, the number of options at the next moment, and so on, we always use multiplication to glue them together. So if we multiply that together, we get 5 times 5 times 5 times 4, which we can check on our calculator. 5 times 5 times 5 times 4 should give us 500. So what does this mean? This means there's 500 different ways that this slot machine could look. What do I mean by that? Well, that means things like coming up with spade, club, spade, blue X, right? That would be one of the ways that the wheel could look. Or maybe it comes up diamond, diamond, spade, green X. Or maybe it comes up heart, heart, club, and jackpot, right? We're saying there's 5 choices here, 5 choices here, 5 choices here, and 4 more choices there. That's 500 different ways that the wheel could look. All right, now we know this. This will be the denominator for all of these probabilities because this is the total number of things that can happen. How many ways can we get $3 signs and a jackpot? Well, if you think about it, the only way, since the dollar signs can only appear on the first 3 wheels, it would have to come $, $, and then the jackpot. That's the only way we could end up with $3 signs and a jackpot. You might say, why can't we get the jackpot first? Well, remember, the first 3 wheels only have the spade, club, diamond, heart, and $ images. So the jackpot, if it's going to show up, has to show up at the end. All right, so that means this probability should be 1 out of 500. There's only one way for this to happen out of the 500 total that we find. All right, what about 3 diamonds and a jackpot? Well, again, we can sort of write out what that would look like. It would have to come up as a diamond, a diamond, a diamond, and then another, and then at the end, the jackpot. Again, the jackpot can't show up on any of these wheels because only the last wheel has a jackpot, and the diamonds can't show up at the end because, well, the 4th wheel only has either X's or a jackpot. So this one would also be 1 out of 500. All right, what about this? $2 signs, a diamond, or a jackpot? Well, this one, there are some different ways to do it. If you think about it, you could get a couple dollar signs, and then a diamond, and then the jackpot. Or maybe you could get a dollar sign, then a diamond, then a dollar sign, and then the jackpot. Or you could start with the diamond, then get $2 signs, and a jackpot. These give us 3 different ways where we would end up with $2 signs, a single diamond, and a jackpot. Notice that the jackpot is always at the end, because that's the only spot it can be, but the dollar sign and diamond can be moved around. So we're just writing out those couple basic ones to count that. That means the probability here would be 3 out of 500. 3 different ways out of the 500 achieve $2 signs, a diamond, and a jackpot. All right, now we're at the otherwise. Well, remember, the otherwise is everything else. So we don't need to make a giant list, right? That would be way too complicated. Instead, we just take these things away from the overall amount. So there was 1, 2, and 5. So we've used up 5 out of the 500 ways. That means the remaining 495 out of 500 are ways that you lose. You can check now that by doing that, these probabilities do sum up to 1 because we have 1, 2, 5, and then 500. So this is a true probability model here. Okay, so notice that this was a little bit more complicated than the previous one because we had to sort of count up all the different things that could happen using our counting knowledge and then actually make a little diagram for these individual outcomes until we got to the last one where we just used the fact that everything had to add up to 1 overall. Now that we have this probability model, though, this question should be very similar to the previous one because once we have the probability model, we can answer things in almost the same manner. So let's see what part B was. Part B says that you want to calculate the probability that you win money on one play. So probability win money on one play. Notice it doesn't say that we care about how much you win. So the 200, the 150, and the 50 are all good to us. So notice that we could just add those probabilities together. So this would be 1 out of 500 plus 1 out of 500 plus 3 out of 500, which would give us 5 out of 500. If we wanted to, we could also change that into a decimal, and you could see that that is equal to 0.01, meaning that there's only a 1% chance that if we had to play this machine just one time, that we would win. Another way to say that is if you had your very last dollar and you were sitting in front of the slot machine, you only have a 1% chance of winning any money if you're going to just play once. All right, let's calculate in C, which is another probability. We want to calculate the probability that you lose money on 30 plays in a row. So you go on a 30-game losing streak. So let's see how we would do that here. So lose money on 30 plays in a row. So we're going to use the same technique since it says that 30 plays in a row. We're going to look at the probability you lose money on one play, and then we're going to raise that to the 30th power because we have to have this happen 30 times in a row, which means we have to multiply that probability with itself 30 times. How do we actually calculate the probability you lose money on a single play? Well, there's only one way to lose right here. You just always end up losing that $1, and that probability was 495 out of 500. So this will be 495 out of 500, all raised to the 30th. We can type that into our calculator to get a nice decimal. So 495 divided by 500 inside of parentheses raised to the 30th. And we should get that that comes out as approximately 0.740. In other words, there's a 74% chance that if you were going to play this machine 30 times in a row, you would lose every time, which of course would mean that ultimately you're down $30 because you've lost $1 every time. All right, at this point, we're now ready to move on from the probabilities and actually start looking at the expected value. So D says we want to calculate the expected value, interpret what this means, and then talk about whether or not this is a good or bad game to play. Considering that it's a slot machine, that probably means it's a bad game because as we know, casinos never make a game that are good for people to play, but let's go ahead and calculate that anyway. So for calculating the expected value, it's going to be the same as what we did in the previous problem. We're going to take each of these outcomes, multiply them with their associated probability, and then sum them all up. So we'll take 200 times its probability of 1 out of 500 plus 150 times its probability of 1 out of 500 plus 50 times its probability of 3 out of 500 plus minus 1 times its probability of 495 out of 500. Now we can just go ahead and put that into our calculator. So 200 times that 1 over 500 plus that 150 over 500 plus that 3 times 150 out of 500 minus that 495 out of 500. And it looks like we should get 0.01 there. So let's just make sure. Yep, there we go. All right, so what does this actually mean here? Well, notice we actually got a positive expected value. So this actually means this is a good game to play. So this expected value is greater than 0, which means this is a good game to play. So in other words, even though we lose like 99% of the time, right? That's what we found, right? 495 out of 500 is 0.99. The payoffs are high enough that they cause this to still be a good game to play. It's going to mean that we're going to lose a lot, but when we do win, we win enough to make up for those losses. So this is a good game to play. How good? Well, we can translate this. We expect to win. Well, if we translate this into money, 0.01 is 1 cent per play on average. So in other words, as we play this more and more, we're expecting that after we add up all our wins and losses, we're averaging about a gain of 1 cent per play. Alrighty, let's go ahead and think about this expected value in another way. So part E says, let's go ahead and interpret this expected value if you played this game 1,000 times. So how do we do this? Well, we want to know the expected value after 1,000 plays. Well, remember, we basically said that we expect to gain 1 cent per play on average, and we're going to play 1,000 times. So all we need to do here is do 1,000 plays times the 0.01 per play, which is our expected value. So let's go ahead and multiply that out. So 1,000 times 0.01, and that should be 10. So we expect to be up around $10 after 1,000 plays. So the idea here, again, is that the language in D that's so important is that we say on average, and the language in E that's so important is that we say around. So what are we really saying here? Well, we're saying that if you play 1,000 times, you're probably going to go on some long losing streaks, right? We said that the chance you lose 30 times in a row is like 74%. So you're going to go on these long losing streaks, but every once in a while, you're going to win some money, right? And that money might be $50, $150, or $200. That's going to sort of make up for those long losing streaks where you keep losing $1 and $1. And after you've played 1,000 times, you should be up somewhere around $10. Now, since this is a good game, the more and more you play, the better and better it is for you, because overall, the game is structured in this case to be a good game for you to play. So if you play more times, we expect you to be up more money as time goes on. All right, let's finish this up then and talk about how we would need to adjust this $3 sign and jackpot to actually make the game fair. Now, since we know it's a good game, we know that this is going to have to be lowered to make it fair. All right, what does officially or mathematically fair actually mean? Well, remember that fair means that the expected value is supposed to be 0. It doesn't mean that each person or each side has an equal chance of winning, an equal probability of winning. It means that the value of the game is 0, meaning that when we take the probabilities and the values in consideration together, then the expected value should be 0. So how do we do this? Well, what we're going to do is we're going to set up this equation, but we're going to say, since we're adjusting this one, that this should become our variable. And of course, we're going to let this expected value be 0 here. So we're going to set up the equation 0 is x times 1 over 500, since we're adjusting that one. And everything else, the $150 payout, the $50 payout, the loss of $1, we're not going to change any of that. So we're going to have 150, 1 over 500, plus 50 times 3 over 500, minus 1, plus minus 1, 495 over 500. Now, you can solve this any way you like, but, to use a little bit of algebra, everything has that 500 in the denominator. So let's multiply both sides by 500. So times by 500. Now, of course, that's a nice trick to do because this side is 0, and 0 times anything is still going to be 0. The 500 here is going to cancel with that, so we'll have x times 1, which will just be x. The 500 will cancel here, so we'll have 150 times 1, which is 150. When we distribute this 500 onto here, this will cancel here, and we'll have 50 times 3, which is 150 as well. And then when we have this 500 distribute here, it'll cancel here, and we'll have minus 1 times 495, so we'll get minus 495. Put all that together, and we should get 150 plus 150 minus 495, and we get x minus 195. Add the 195 over and we get 195 equals x. What does that tell us? Well, that tells us the $3 and jackpot should pay 195 to make the game fair. And notice that matches our prediction because that's a little bit lower than the initial setup. The initial setup said you win $200, and we're saying to make the game fair, you would only pay $195. Since it was initially set up to be $200, which is above $195, it was a good game to play. If they lowered it down to $195, it would be a fair game. Not meaning that each side has an equal chance of winning, but meaning that if you played it for a long, long time, you would basically break even. If you paid less than $195 for the $3 sign and jackpot, it would be a bad game to play, and you would be losing money to the casino. All right, so this is definitely a more complicated sort of expected value situation, but the main idea here is that anytime you see these sort of slot machines or these wheels, you want to use this counting approach to get the total. You can make certain little diagrams or some little notes to figure out the individual probabilities, and then once you're in here, this part always proceeds the same. The expected value formula doesn't matter how you got the probability model, the expected value formula is always the same. You take each of the values, multiply them with their probabilities, and then sum them all up. All right, let's go ahead and look at one final expected value example, which uses the binomial, a completely different sort of probability structure, to build the probability model. However, once again, even though this initial part will be very different, once again, you'll see that once we get down into the expected value, it'll proceed the exact same way. All right, so for question 3, we're going to say, suppose you have a carnival and there is a balloon popping game. So in this game, you pay $8 just to get to play, and then you get to throw 4 darts at balloons. You know that each time you throw a dart, there's a 45% chance you'll pop a balloon, and each throw is independent. Remember, this is a big keyword right here. As soon as you see that word independent, you're thinking about this being binomial, and we'll check that in just a moment. Then the way that the prizes for this game works are as follows. If you pop all 4 of the balloons, so every one of your throws pops a balloon, well, then you win a big prize that is worth $25. If you pop 3 of the balloons, you win a medium prize, which is worth $15. If you pop 2 balloons, you win a small prize worth $10. If you only pop 1 balloon, or if you don't hit any of the balloons, you win nothing. Now you might say, well, if you win nothing, that's not bad. But remember, all of these involve also paying $8. So we'll also have to be careful here about adjusting what the value of each of these are, considering that you have to pay $8 just to play. But let's first start by thinking about this, whether or not this is going to be binomial. So remember, binomial means that it has to have 2 outcomes, which makes sense, right? Each time you throw that dart, you either pop a balloon or you don't. So there are only 2 outcomes. It needs to be independent, which the problem tells us it is. And then we need to know the number of trials, or the number of attempts, and the probability of success. Well, remember, when you pay $8, you get to throw 4 darts, so you know you get 4 tries. And we know the probability of success is 45%, or 0.45. Remember, sometimes we also like to include what is the probability of failure, so 1 minus p here. Well, 1 minus 0.45 is 0.55. So in other words, if you have a 45% chance of popping a balloon on a single throw, you have a 55% chance of not popping a balloon. Okay, now that we have that and we know that it's binomial, let's go ahead and actually see what we're supposed to do with this one. So for question 3, we're going to again construct a probability model, answer a few probability questions, and then move on to the expected value. So let's start with the probability model here. Okay, so probability model. So what are the outcomes? Well, you can pop 4, you can pop 3, pop 2, or otherwise. Now let's think about what these are worth. So when you pop 4, you win a prize that is worth $25. So you can sort of imagine the person gives you $25. Now does that mean that you've gained $25? Well, in this case, we have to include the fact that they said that you have to pay $8 to play. So you give them $8, and if you pop all 4, they give you basically back 25. So what does that actually mean for you? Well, this can be viewed as plus 17. You give them $8, and then you pop 4 balloons, they give you 25. That means you've gained $17. For this one here, you pop 3 balloons. They give you $15, but remember you already gave them 8. So from your perspective, that's only plus 7. For this one here, you pop 2 balloons. They give you $10, but for your perspective, that's only a gain of $2. Then what about here when you win nothing? Well, from your perspective, that means you actually end up losing $8. So notice that we had to be careful here, and we had to modify each of these outcomes by the amount that it costs to play the game. Now you might say, why didn't we do that back here? We just left these sort of alone. Well, the reason is here is that these were already factored in. Notice there's no mention in the question of it costing anything to play, which means that we can assume that this has already got that built in. A good way, sort of a nice little trick for checking that, is to look at the otherwise. Notice that the otherwise already had you losing $1, meaning the cost must be factored in. Here, the otherwise had you winning nothing, which means that the cost hasn't been factored in yet. We had to make sure we modified that. So something to be careful with there. Okay, now how are we going to get these probabilities? Well, we said that we want to use that binomial. So for each of these, we're going to use our binomial formula, which we know we're allowed to do because there's 2 outcomes, it's independent, and we know the number of trials and the probability of success. So to get this best outcome where you win the big prize, you have to be successful on all 4. So we know from our binomial formula, that'll be 4C4. We have 4 attempts and we want 4 successes. The probability of success, which is 0.45 to the 4, and the probability of failure, 0.55 to the 0, because if we only have 4 tries and we have to be successful on all 4, we can only have 0 failures. Putting that into the calculator, remember that this is actually just equivalent to 1, as is this. So this guy we could have just simply written as 0.45 to the 4. These components only matter for where you actually have some failures, but we can type in the full formula if we want to. Either way, we should end up where this is approximately 0.041. So in other words, if you go to play this game, you have about a 4% chance that you hit all 4 balloons and you end up winning the big prize. What about this one here? Well, for this one, we would have 4C3, 4 attempts. We need 3 successes, 0.45 to the 3rd, 0.55 to the 1. So here we're saying we get 3 successes and 1 failure. Typing that into our calculator, we should get, looks like about approximately 0.200. So in other words, there's about a 20% chance that you would hit 3 of the 4 balloons and end up with the medium prize. All right, let's look at this one. This would be 4C2 because you have to have 2 successes, 0.45 to the 2, but since you have 4 attempts, that means you also have 2 failures. So 2 successes, 2 failures. Typing that into our calculator, 4C2, then times 0.45 squared, and then times 0.55 squared. Well, then we should get that that is approximately 0.368. So in other words, there's about a 36.8% chance that you would make 2 of the 4 throws and end up with the small prize. Now, what about this otherwise? Well, there's 2 ways we could do it. We could say that the otherwise is actually popping 1 or popping 0. So we could do things like 4C1, 0.45 to the 1, 0.55 to the 3, plus 4C0, 0.45 to the 0, 0.55 to the 4, where this is hitting 1 and this is hitting 0. But that's really unnecessary because remember, this has to be a probability model. So whatever the overall probability that remains is the probability that you lose. So we can do this as 1 minus the sum of all these other ones. So because this is our last option, we're using what we called in when we were studying probability as the complement rule. Add all these up, take them away from 1, and whatever remains is your probability of the last outcome. So make sure to use your parentheses there. 1 minus parentheses 0.041 plus 0.200 plus 0.368. Close it up, and you'll see that the chance that you lose is 0.391. So in other words, the chance that we end up either hitting 1 balloon or no balloons, in other words, the chance that we end up not winning any sort of prize is about 39% here. All right, now that we have that probability model, we can go ahead and look at some of the follow-up probability questions. So for B, we wanted to calculate the probability that you win a prize when playing this game once. So let's go ahead and see that. So probability win prize on one play. So maybe you're only going to play this game once. What's the chance that you walk away with a prize? Notice we don't care what type of prize. We're just saying any prize. So we're just going to add these probabilities together. 0.041 plus 0.200 plus 0.368. We put all that together and we should get 0.609. Let's just check that. 0.041 plus 0.200 plus 0.368. 0.609. So in other words, you have about a 60.9% chance, or about a 61% chance, that if you sit down and you play this game just once, meaning you make all four you just get to throw 4 times, that you end up walking away with some prize. Maybe a small one, maybe a medium one, maybe a big one. We're just saying a 61% chance, basically, of getting some sort of prize. All right. Part C. Part C says, calculate the probability that you win a prize 4 times in a row. So it's going to be related to what we just did there. So we want the probability you win a prize on 4 plays in a row. So notice that we have this 4 plays in a row. So we will say that this is the same as the probability of winning a prize on 1 play. And then we have to repeat that 4 times in a row. So we raise that to the 4th power. Now this time, winning a prize on 1 play, we just calculated that right here. So we will do this as 0.609, and we'll raise that to the 4th power. So 0.609 raised to the 4th, and what we should get there is approximately 0.138. So while we have about a 61% chance that we would win a prize on 1 play, the chance that we would go on like a 4-play winning streak, where we get 4 prizes in a row, is only about 14%, which makes sense, right? We're pretty good at winning a prize, about over half the time, but to do that 4 times in a row, much harder. All right, now let's go ahead and look at D. So for D, we want to actually go ahead and now calculate the expected value and then decide if this is a good or bad game, as is standard. So remember, to do this, we use the values that we have here and multiply them with their probabilities and then sum them up. So the expected value here is going to be that 17 times the probability, which is 0.041, plus the 7 times the probability, 0.200, plus the 2 times 0.368, plus the minus 8 times 0.391. And of course, we got to make sure we have that negative there, because if this happens, we're losing money overall. This is something we definitely want to just feed through the calculator. So let's see what we end up getting. So 17 times 0.041 plus 7 times 0.200 plus 2 times 0.368 plus negative 8 times 0.391. And looks like ultimately what we should end up getting there is negative 0.295. So what we're getting overall is that we get a negative expected value here. So what does that negative expected value indicate? Well, of course, that tells us that this is a bad game. So the expected value here is less than 0, which implies that this is a bad game to play. So from our perspective, even though we have a pretty solid chance of winning a prize in terms of how much the prizes are worth, it's not a high, these things are not worth enough to compensate for the fact that we lose quite a bit of money if we don't get a prize. So overall, this is a bad game to play. And of course, we can say how bad. If we change this into cents, we can say this is about 29.5 cents. So we expect to lose 29.5 cents per play on average. Now, a couple things to mention here. Again, notice that when we say that we lose, we don't need to include the negative because the losing indicates that that would be negative there. Again, notice we're also using that language of on average. We never actually lose 29.5 cents. We either end up gaining $17, gaining $7, gaining $2, or losing $8. Those are the only things that can sort of happen. But we're saying on average, we expect to lose about 29.5 cents per play. The other thing to sort of just keep in mind here is that this is basically measuring how bad of a game it is to play. As soon as it's negative, we know that it's bad, but this tells us basically how bad. All right, let's go ahead and finish this up by talking about the expected value with a bunch of plays. So let's imagine we're going to play this thing 80 times. What do we expect to have happen here? So we now want to know the expected value after 80 plays. So remember, this is what we expect to have happen per play. So we're going to take our 80 plays and then times our negative 0.295 per play. So we multiply those together, that 80 times negative 0.295, and we should get that comes out as about negative 23.6. So after 80 plays, we expect to be down around $23.60. So again, what this is really telling us is that if you play this game once, you have about a 61% chance of winning a prize and about a 39% chance of not winning a prize. But the longer you go on to play, because it is fundamentally a bad game, the more and more you expect to be down. So somebody could get lucky on a single play and win, but as people in general play more and more, their overall losses are going to pile up above their gains. And after 80 some plays, we expect, even though you've won some, you've lost some, your overall winnings and losses put together should mean that you're down somewhere around $23.60. Again, it's just an approximation. It would be what happens in the long run, so we want to make sure we have that word around there. Okay, so questions 1, 2, and 3 here all dealt with the expected value in different ways. So notice that at the beginning of the question, the way we set up the probability model in this situation was very different than what we did in question 1 and question 2 because it was binomial. But once we had that probability model, things proceeded very similarly. The expected value is easy to determine once that probability model is in place. So while building the probability model can shift from problem to problem, this practice basically showed you the 3 main ways you'd be expected to build the probability model. Sort of very simple in question 1, using some of the counting stuff in question 2, or using the binomial in question 3. Once you have that probability model, the expected value will always proceed the same way. All right, let's get to the last question on this practice, which dealt with the sort of different topic from expected value. Remember, expected value is sort of an extension of probability. The sampling distribution, however, is really the sort of gateway into the second half of our entire semester as we move into inferential statistics. So let's talk a little bit about question 4, which dealt with the sampling distribution. So for question 4 here, we have this, we're looking at the revenue that a food truck makes per day, and we have this information that it is normally distributed. If you think way back to the beginning of our course where we first worked with the normal distribution, we know it's a huge amount of information if you know something is normally distributed, because if something is normally distributed, all you need to know everything there is to know about that population is the mean and standard deviation. And in this case, we know the mean is 925, and we know the standard deviation is 300. So let's go ahead and answer each of these questions here. So for part A, we want to find the probability that on a randomly selected day, the food truck makes less than $700 of revenue. So for part A, we want probability 1 day less than $700. Okay, so how are we going to do this? Well, it's a single day, so we're just going to take the information that we were given here and proceed like we did at the beginning of our course, drawing a bell-shaped curve, calculating the z-score, and going from there. So let's go ahead and draw our bell-shaped curve, which we know we can do because it's normally distributed. The mean is 925, so we'll go ahead and put 925 in the middle. We want the chance that the 1 day is less than 700. So 700 is somewhere over here. And we want less than 700, so we'll be shading in to the left there. Now to actually find that, we can go ahead and calculate our z, which will be our data point 700 minus the average 925 divided by the standard deviation. Standard deviation here was 300. So let's put our 300 there. If we go ahead and we calculate that, if we do the numerator first, 700 minus 925, looks like we should get negative 225 divided by 300. Then we go ahead and do that division, and we get that our z here is equal to negative 0.75. All right, let's go ahead and look that up on table A now. So remember, table A translates us from a z-score, which measures the position, into a proportion or an area that tells us the area under the curve to the left. So let's go ahead and look at table A. We're looking for, again, z of 0, negative 0.75. So we'll zoom out a little bit. There's negative 0.7. There's the 0.5. So we intersect those together. And it looks like what we should have there is this guy right there. Okay, so 0.2266. So in other words, right here, we get 0.2266. All right, now if we draw that onto our table, remember, whenever you look up something on table A, it always tells you the stuff to the left, so 0.2266. Notice that in this case, that does match up to it, so that gives us our probability. So the probability that on a single day, they make less than $700 is equal to 0.2266. Now, you might ask yourself, was there anything new in this question? Well, no. If you were comfortable back when we did this at the beginning of our course and we calculated proportions or percentages based on the normal distribution, this was the same thing. A lot of times at the beginning of our course, we would go ahead and translate this as a percentage and say 22.66. But since it just said probability, you could certainly do that if you wanted to, but you're also free to just leave it as a decimal here. All right, let's go ahead and look at B, which is also some review here. So if we go ahead and do B. So B says that on a particular day, the food truck makes revenue that places it at the 85th percentile, and we want to know how much revenue did the truck make. So this is what we call the sort of reverse process. Why is this the reverse? Well, because in this case, we know its sort of percentage rank or its position, and we want to know the actual value of the variable. So we can do this by sort of drawing our diagram. There's the 925. This particular day is at the 85th percentile, so it is certainly above average. So we'll put it somewhere over here. We'll call it X. And of course, this shaded area here, which is all the days that we made more money than this, or less money than this, right? Or that this day made more than. Well, we know that this has to match the percentile rank, which is 0.85. So in other words, if this day is a day where we're at the 85th percentile, then 85% of other days have to make less money than this day. Okay, so what do we do with this then? Well, now what we want to do is we want to take, I'll use this a different color here. We want to take this and we want to find closest value 0.85 inside table A. So we're going to be looking inside of table A. Remember, this 0.85 is not a z-score. We want to look it up and find the corresponding z-score. So let's go ahead and take a look. So it should be somewhere over in the positive side because we're above average. I see some 0.85s here. There's 0.8531, 0.8508, 0.8485. This guy is a little bit closer, 0.8508. So this is the closest thing. If we expand out then, we can see that this gives us a z of 1.04. So that tells us that the corresponding z-score should be z equals 1.04. So in other words, to be at the 85th percentile, that means our z-score needs to be 1.04. Now we can go ahead and set up our equation. 1.04 is the z. We don't know the x, minus the 925 divided by the 300. Then we can solve this by multiplying the 300 over. So 1.04 times 300 gives us 312 equals x minus 925. And then we add the 925 over, and we get 1237 equals x. So the truck made about $1,237 that day. So in other words, a day in which they make $1,237 would be a day that would put them at the 85th percentile. In other words, that's a day that is better than 85% of the other days in terms of revenue for this truck. So A and B here, you'll notice these were just review questions back from when we initially worked on the normal distribution. What sort of tells us that they're review questions? Well, the main thing is that when we initially worked with the normal distribution, we always just talked about a single individual. And you'll notice that in A, we were talking about a randomly selected day, a single day. Same thing here, on a particular day. Now, C, D, and E will all be sort of newer things because they start to talk about groups of days. 3 randomly selected days, 3 randomly selected days, 7 days. So as soon as we start introducing groups of days, that puts us into sort of our newer material. So let's go ahead and give ourselves a fresh page, and let's look at C. So for C, we want the probability that on 3 randomly selected days, the food truck makes an average revenue less than 700. Now, the key thing we're going to see here is this word average. As soon as you see that mentioned, that means you want to use your sampling distribution. So for part C, we want the probability that 3 days average less than 700. So again, as soon as you see that word average here, that tells you to use the sampling distribution. Now, the sampling distribution has to come with a sample size. So how big is our little sample here? Well, it's saying 3 days are supposed to average less than 700. So this would be the sampling distribution with n equals 3. Now, when we say use the sampling distribution, this means it's a new distribution. So we need to know its mean, its standard deviation, and its shape. In terms of notation, we usually use a little subscript with an x bar to indicate we're talking about the sampling distribution. And remember, we know everything there is to know about the sampling distribution based on the population via the central limit theorem. So the mean stays the same. So the mean of the population was 925. So the mean of the sampling distribution will be 925. The standard deviation, remember, changes. It's the original standard deviation divided by the square root of n. So the original standard deviation was 300. So we will have 300 divided by the square root of n. The n here is 3 because we're talking about a group of 3 days. So square root of 3. If we do that, 300 divided by square root 3, we should get that comes out as about 173.2. So remember, groups always show less variation than individuals. So while individual days had a deviation of $300, groups of 3 only have a deviation on average of $173. So groups always show less variation. And the shape, well, remember that the central limit theorem in broad strokes says that the sampling distribution is always more normal. In this case, our population was already normal, so the sampling distribution of any size, doesn't matter if it's n equals 2, 50, or 100, because the population was normal, the sampling distribution will still be more normal. So still normal. Okay, so now we have our sampling distribution, which is going to allow us to answer this. So this is the information we're going to work with. Since it's still normal, we can draw our bell-shaped curve. We can put the middle at 925 because that's where the mean is. We're looking at less than 700, so 700 is over here. Less than 700 means we're shading into the left here. Let's go ahead and get our z-score. So z in this case is going to be 700 minus the 925 divided by the standard deviation. Is the standard deviation 300? No, because we're working with this group of 3 days. So we'll use this new standard deviation of 173.2. We'll go ahead and do that. We have minus 225 over 173.2. Let's go ahead and do that. Negative 225 divided by 173.2. And it looks like we should get z here. It is about negative 1.30. Because remember, we always round z-scores to 2 decimal places. All right, let's go ahead and look this up on table A then. So if we go ahead and do that, negative 1.30. So there's negative 1.3. And there's the 0, so putting those together, right there, 0.0968. So once we do that, we get 0.0968. Remember, table A always tells us what's to the left, so this does match up exactly with what we wanted shaded. So in this case, we can say that the probability that 3 days have an average less than $700 is 0.0968. So in other words, if they're looking at this, if this food truck is analyzing their profit over 3-day periods, the chance that they would have an average over a 3-day period of less than $700 is a little under 10%. Remember, an average being under $700 doesn't mean that every day is under 700. It means that they might have a day where they make like 650, a day where they make like 720, and another day where they make 580. Put those 3 days together, and they're averaging less than 700, even though one of the days they might have made slightly over 700. So this is about the average being less than 700. Again, keyword here, if you see average, you know you need to use that sampling distribution. All right, let's go ahead. And we'll do D over here. So what about D? Well, D is also about a group, but it's a little bit different. For D, we are still looking at 3 randomly selected days, but it says makes less than $700 of revenue on all of these days. So here we want the probability that 3 days are all below 700. So how do we do this? Well, the key word in this case is that all. And we do this just like we did some of those expected value ones earlier. If they all have to be less than 700, then we can translate this as the probability that one day is less than $700. And then we need to repeat that 3 times. We take that probability and we raise it to the 3rd power. In other words, we multiply it with itself 3 times for it to happen on the 1st day, the 2nd day, and then the 3rd day. So in other words, notice that if you see this word all, you use this multiplication rule, this power, this exponent to handle this probability. Now, how do we get the probability that one day is less than $700? Well, we could go ahead and use the normal distribution again, but remember, this is exactly what we answered in part A, one day being less than $700. It was 0.2266. So let's go ahead and put that in, 0.2266. Still need to raise it to the 3rd power or multiply it with itself 3 times. So we go ahead and we do that, and we get approximately 0.0116. So notice there's only about a 1% chance that they would have 3 days in a row where they make less than $700. Now again, notice if you watch the sort of videos about the sampling distribution, you'll notice that this is sort of standard here, right? For a single day to be less than $700, the probability was low-ish, about 22, 23%, but not super rare. For there to be an average less than $700, okay, that's harder to do because you have to have it happen sort of over the course of 3 days. It was about 10%. And to have it happen 3 days in a row, that should be the most rare. And it was, because the probability is only about 1%. All right, we've got one last piece here. So for part E, we are looking at a group of 7 days, and we want to know that if the food truck makes a total revenue less than $5,600. So let's go ahead and we'll do that right here. So for part E, we want the probability 7 days total less than 5,600. So whenever you see this word total in here, what you need to do is you need to translate this into an average. So a total of 5,600 over 7 days is equal to, well, if it's $5,600 over 7 days, it tells us that this is equivalent to an average of 5,600 divided by 7, which, if we check on our calculator, 5,600 divided by 7 is 800 over 7 days. So if your total is supposed to be less than 5,600 over 7 days, that's the same as saying your average is less than 800 over those 7 days. So we're going to actually work on the problem that we want the probability that over 7 days the average is less than 800. So just to go back over this, the key idea here is that anytime you see mention of the word total, what you want to do is you want to translate from total to average. Notice it's still going to be over the same time period or the same size, 7 days in this case. But the change is, instead of talking about the total of those 7 days, we're going to talk about the average per day. If this moment where we did this division is a little confusing, sort of think about it like this. If you and, say, 4 friends, so 5 people, are going somewhere and you need $500, you don't all have to bring exactly $100. You need to bring an average of $100 each, so that when you put all your money together, Well, if the average is $100 and 5 people, that means in total you'll have those $500. Even though you might only bring $80, if somebody else brings 120, they can sort of compensate for you. So this is why we translate from total into average. Okay, now how do we approach this? Well, since we have this word average here, that means we do the sampling distribution. Now you might say to yourself, well, that means we just use all this stuff here. Well, we have to be very careful though, because remember the sampling distribution comes with the sample size. Back up here, we did the sampling distribution for n equals 3. Here though, because we're talking about a week, the n should be equal to 7. So it's going to have some different features here. So the mean is still going to be 925, because remember the mean never changes. For the standard deviation, remember it's the original standard deviation divided by square root of n. That's 300, but this time divided by square root of 7. If we calculate that, 300 divided by square root of 7, we should get that is 113.4. So notice a smaller standard deviation because we're talking about a bigger group size. And the shape, well, again, if the population is normal, the sampling distribution will always be normal. So this is still normal. All right, now we can go ahead, draw our bell-shaped curve. We have our mean at 925. We're interested in less than 800. So 800 is somewhere over here. And of course, less than 800 means that we're shading in to the left here. Okay. Let's go ahead and calculate our z-score. So our z would be our observation, 800, minus the 925, which is our mean, divided by our standard deviation, which in this case is supposed to be 113.4. If we go ahead and do that, we're going to have minus 125 over 113.4. And if we do that, we should get that that comes out as being approximately negative 1.10. Now we can go ahead and we can find that on table A. Oh, that yellow is not going to work there. Let's go with this guy here. So let's look this up on table A. So negative 1.10. So there's negative 1.1 and 0. So we're using this guy here, and that gives us 1.1357. So we find 0.1357. Now again, table A always tells us what's to the left, which it does match up here. So 1.1357. So that tells us that the probability that 7 days have an average less than 800 is 0.1357, but that's also, as we saw, equivalent to the chance that the total it has less than 5,600. So the probability that 7 days have a total under 5,600 is equal to 0.1357. So the key thing in this sort of example here is that while the question was about the total, we translated that total into an average and then used the sampling distribution. Now, when we write our final answer, you could say that this is this or this, but they are equivalent. That's the whole point here. So if you're ever asked a question about a total, you always want to translate it into a statement about the average. And then since it's a statement about the average, you use the sampling distribution. Do be careful though, because as we saw here in part C, we were talking about the average of a group of 3. So we had the sampling distribution with n equals 3, and that is very different than the sampling distribution with n equals 7, because if the sample size changes, then that standard deviation is going to change. Well, this wraps up practice 7, and that's the end of this.